Assalamualaikum and selamat sejahtera. In the last video, I have explained how to sketch voltage and current waveforms of single-phase uncontrolled rectifiers with resistive loads. This time, we will analyze the waveforms based on the general parameters of the rectifiers. Before we start the analysis, it is good to consider the ideal waveforms of the output voltage and output current of the rectifiers. The black line and the red line are referring to the ideal waveforms of the output voltage and output current respectively. These waveforms are called ripple-free waveform, and they represent the average or DC components of the AC supply converted by the rectifier. Unfortunately, without any filters, the rectifiers can generate the ideal voltage and current waveforms. In the last video, we have seen that the output voltage and output current waveforms generated by both half-wave and full-wave rectifiers are not constant. These waveforms consist of voltage or current ripples due to the existence of AC components at different frequencies. Based on Fourier series, the AC components are called harmonic components. Usually, when we want to design a filter, we can use the information related to the harmonic components. Other than that, the ratio between the harmonic and the DC components represents the ripple factor of the waveforms. Ideally, the ripple factor should equal to 0. Moreover, the rectification ratio or the efficiency of the rectifier is also affected by the ripple waveforms. In ideal condition, the efficiency of the rectifiers is 100%. Now, let's analyze the output voltage waveform of a single-phase uncontrolled half-wave rectifier. First, we start with the calculation of the average output voltage using this general equation. According to the equation, we need to determine the full period of a complete cycle of the output voltage waveform. Based on the wave shape of the output voltage, we can identify that the full period, which is T, is equal to 2 pi. Hence, we can rewrite the general equation by replacing the T with 2 pi. However, since the area under the graph can be calculated between 0 until pi, therefore, this T should equal to pi only. Based on a complete derivation of the equation, therefore, the average output voltage is equal to Vm per pi. Next, we can sketch the waveform of the average output voltage as follows. To find the RMS output voltage, we can use this general equation. Based on the final equation, we can see that the RMS output voltage of this rectifier is equal to half of the peak amplitude of the output voltage waveform. Thus, we can sketch the waveform as follows. Next, we can use the average and RMS output voltage values to calculate the ripple factor of the waveform. By assuming that the peak amplitude is equal to 1, therefore, the percentage of ripple factor is equal to 121%. Meanwhile, the efficiency of the rectifier is only 41%. For a single-phase uncontrolled full-wave rectifier, we can calculate its average and RMS output voltages using the same general equations applied in the half-wave rectifier. However, based on the wave shape of the output voltage waveform, we can see that the full period of a complete cycle of the waveform is only pi. Moreover, according to the wave shape, we can also set the range of the integral in both equations as 0 and pi. By completing the derivation, we can see that the average output voltage of the full wave rectifier is equal to Vm per pi. Meanwhile, the RMS output voltage is equal to Vm divided by SERT2. This equation is the same equation used in calculating the RMS value in single-phase and three-phase systems. Next, based on these equations, we can sketch their waveforms as follows. Finally, the ripple factor and the efficiency of the full wave rectifier are 48% and 81% respectively. Before I proceed to the example question, I want to highlight the differences between half-wave and full-wave rectifiers. Based on this table, we can differentiate them in terms of circuit topology, number of diodes used in the circuits, their principal operation during the positive and negative half cycle of the AC sources, ripple factor, and efficiency. Based on this parameter, we can see that the full wave rectifier has lower ripple factor with high efficiency. Because of this, we can claim that the performance of full wave rectifier is better than the half wave rectifier. Now, let's try to solve one example question. Usually, I will circle all important information given in the problem. From the statement, I know that this problem is related to single-phase, uncontrolled full-wave rectifiers with a resistive load of 25 ohm. The AC source of the rectifier is 230 volt supplied at 50 Hz. And based on this information, we need to find the efficiency and the average diode current of the rectifier. So based on the problems, I will start with the efficiency. It is good to start from the efficiency equation because we will know which parameter values we need to find. Based on the equation, we know now that the efficiency can be calculated using the average and RMS output voltage of the rectifier. To find the average output voltage, always remember to start the calculation with the general equation and the output voltage waveform. Based on the previous discussion, I have taught you how to determine the T values in the equation. As a result, we have this equation. Next, we need to find the peak voltage value. However, the voltage value given in the statement is an RMS value. Therefore, we need to multiply the RMS voltage with Z2 to convert it to peak voltage. Lastly, we can use a calculator to calculate the answer. Next step is the calculation of the RMS output voltage. As usual, always start with the general equation and apply this equation using the calculator. Once we have all parameters value, we can solve equation 1 and find the answer. Based on the solution, the efficiency of the full wave rectifier is 81%. And if we compare this answer with the efficiency in the previous discussion, we can see that both values are the same. Here we can conclude that the efficiency of any single-phase uncontrolled full-wave rectifier with a resistive load is fixed to 81% regardless of the AC supply voltage values. Lastly, it is the average diode current. Based on the previous discussion, you can apply these procedures to find the answer. For this rectifier, the average diode current is 4 ampere. This solution will be the end of my video. As a homework, please complete the derivation of these equations.